Hello, my name is Peter Schubert, and I'm here to talk about wireless power transfer to a Sitallite Stratospheric platform. My co-authors include Erinna van Wynsberghe, AJ Finnell, Christian Salgueiro, and Saket Suri. Most of us are with Indiana University, Purdue University, Indianapolis. Mr. van Wynsberghe is with Van Wyn Aerospace Logistics in Canada. Our motivation is persistent ISR, intelligence, surveillance, and reconnaissance. A Sitallite, a high altitude pseudo-satellite, rests in the stratosphere and is much closer than and much cheaper than a satellite. This is higher than aircraft. This is, has a longer duration than a drone. And from altitudes of 25 kilometers, you can see 500 kilometers in all directions. This gives 1 million square kilometers of persistent observation space. The Sitallite is patented by Van Wyn in the United States. The Sitallite concept is a superpressure balloon. The superpressure balloon is thicker than a weather balloon and has the ability to remain at altitude for a long period of time. At these altitudes, the atmosphere is about 1/100th that on the Earth at sea level. The temperature is about -40 degrees, and these light winds of 10 to 30 meters per second will push these Sitellites around. So the patent says to use plasma air thrusters. These will ionize the air that is available at that altitude and then use electric fields to propel those and use that for station keeping as well as for limited amounts of translation. So this requires beaming power wirelessly from the ground in order to provide the consistency of station keeping at that location. In this manner, there's no batteries required, there's no energy storage required on the device, although there might still be some amount just for limited periods of occlusion, but it can have a very long duration measured in many months, maybe even a year. This is a one-line diagram of the ground station system diagram. This is essentially to lay flat on the ground underneath the Sitallite location and shows a diesel generator. So this study is aimed at a remote location where the grid is not available. This is more expensive than doing it where there is a grid available, but our cost studies assume that this was in, for example, the Arctic or the Antarctic, where satellites have a very difficult time maintaining a station keeping. Next, we have the transmit antenna sizing study. And the first important thing on the left here is the directivity of the transmit antenna. It increases steadily as a function of the number of elements that are in this. So a larger phased array antenna has a greater directivity, a greater gain. Because of this, the graph on the right shows 3 different antenna studies, 60, 80, and 100 meter diameter Rectennas. And so we picked the 80 meter diameter Rectenna as a reference case, that being about the largest size that's currently conceivable for a superpressure balloon. What we found from the study is that smaller antennas have less directivity, therefore they have higher total power, and because they're smaller, that also means a much higher power density. So there is an optimum to be found in the sizing for such systems. The illustration at the bottom left shows one possible configuration for this in an Arctic environment. So this remote location being fueled by diesel generators turns out to dominate the cost. In the bottom right, we have a pie chart with the total transmitter costs. And you can see on the left and bottom sides, the generators and diesel fuel together are half of the cost. So this much of the cost can be dramatically reduced if there's a grid available with plenty of power available for this. Also note that the phase shifters are a very expensive component for this, and this is an area for improvement in the economics of the field of wireless power transfer. This study shows the characterization of an optimum for the ground station. The top line in the dark blue has a red dot at the point where the total overall cost is minimized as a function of the transmitter length and the total amount of power being generated. In this and other graphs, the costs are not explicitly listed for business purposes for Van Wyn, but we encourage you to contact Mr. Van Wynsberghe to get more details on costs. This is a cross-sectional schematic of the Sitallite itself. The light blue in the center is a superpressure balloon, and the magenta-colored squares are the plasma thrusters. These would be placed around the periphery of the balloon and be able to spin if needed and to translate as needed to counteract the winds. There's some energy storage shown on the left. That's for short period occlusions. Also to provide heat for the electronics, which at -40°C will generally require a heater. On the right side is shown the controls and then also the payload. We have sizes and weights for those computed. The payload, of course, is what pays for the whole process. So this might be communications or observations as just two examples. Below the balloon, facing towards the ground, is a mechanical structure for the Rectenna. Also a microwave absorber so that we're capturing or at least reflecting back as much of the power as we can. And then the Rectenna itself is the lowermost portion of this configuration. This is a circuit diagram for the Rectenna. This is assuming the brown style of a shunt diode for the rectification process. We looked at a number of commercially available diodes shown here in the center and the bottom, and created a radar chart for the purposes of identifying the one which best suited a particular application. The overall system sizing is superlinear, meaning the larger you make it, it increases more than linear in terms of dollars as well as weight. So a larger size has lower power and greater efficiency, but it has more mass and hence more cost and also smaller payloads. So the reference case selected here is with a Rectenna diameter of 880 meters, and this is the one that was taken forward for this study. Safety considerations are important. One of the technologies that's envisioned for this is the pencil beam technology that was published first in 2016 in the International Astronomical Conference by Peter Schubert, that's by me. And this is a configuration of a phased array antenna which has arbitrarily low side lobes. Because of that, passersby or operators who are close to the side of this transmit antenna will get essentially no stray radiation towards them. In the vertical direction, then we have to worry about passing insects, birds, and planes. And what are shown here are typical heights and power densities and exposure times for each of those. So a commercial airplane at say 30,000 feet might pass through this beam in 0.2 of a second. It's certainly possible to steer around these beams. There probably won't be very many of them because of the 500-kilometer radius for the view. So it should be a very minor change to any kind of flight path to avoid these beams and that very brief duration of interruption on communications. So in conclusion, Sitallite is a high altitude pseudo satellite. It's geostationary. It stays over the same point on Earth. And by using wireless power transfer up to this extreme environment, this now has long duration ISR through the use of these plasma air thrusters. So a 12-month operation is conceivable. At that point, it would be lowered back down under power. The balloon would be checked or replaced. And then the payload can be switched out at that time. Because we're beaming power to this and have some flexibility on the size of the array and the density, then a power-hungry payload might be welcomed. And this is another advantage over orbiting satellites. So the total deployed system costs are less than satellites, especially for remote locations, and it's ideal for polar locations because geostationary Earth orbit satellites are inadequate for this. And we can use self-warming electronics on the ground and in the stratosphere and have some intellectual property developed for that. So this report shows a technical feasibility for wireless power transfer for a long duration ISR via the HAPS with the Sitallite concept. And we certainly invite your questions and comments. This is a list of the references that have been cited, and my contact information is shown here on the bottom. Thank you very much for your attention.